Hello, today we'll be presenting our final presentation on deep visual speech recognition under the supervision of Dr. Hesham Eraqi and Dr. Nouri Sakr. Here is our outline. We'll be covering everything from our initial problem statement to our design and then show you our results and a demo. Over 5% of the world's population is hearing impaired and around 50 million have speech impediments. And yet, most forms of mainstream media do not even offer closed captioning to allow accessibility to these demographics. Even modern forms of communication like phones, video calls, and virtual assistants, which should be accessible to everyone, still do not cater to these populations. Although audio and audiovisual recognition systems are in existence and perform relatively well in certain settings, there is no doubt that their performance significantly drops at any instance where the audio signals deteriorate or are corrupted in any way. Meaning that in situations like noisy environments, for example, the performance of these models is hindered significantly. Meanwhile, what we are proposing here is a model that relies primarily on visual input, meaning that the model is robust regardless of any fluctuations in audio quality. Our motivation for this is because the domain is relatively unexplored. Possible accessibility applications where instead of using sign language, for example, the user could simply point the camera towards their face and it would provide their hearing colleague an audible translation so both parties can easily understand each other. And improving existing technologies such as automatic closed captioning for uncaptioned videos. Our primary goal has always been to contribute to the scientific community by enhancing existing architectures and improving on the state-of-the-art results in the domain. We have to narrow down our research questions as it impacts the possible architectures we should use. We decided on going for a word-based model rather than a sentence-based model, since sentence-based models haven't had a lot of contributions recently and none since 2018, which made us believe that it is quite difficult, especially given the time and resource constraints we have. So we thought it might be better to initially implement our architecture design on word level. Additionally, we decided that our model should be text-based rather than speech-based. This is because speech-based models are not very advanced as of now and depend heavily on the speaker rather than what is being said. It is incredibly difficult for models to learn speaker-specific cues that are essential for inferring accurate speech from lip movements. Thus, text-based models might be more efficient and logical to implement. And according to our research and some initial experiments, we reached the conclusion that our model would be best for word-based and text-based.
The LRW dataset consists of up to 1,000 utterances of 500 different words, divided into folders. Each folder contains different instances of the same class or word, spoken by hundreds of different speakers, with different genders and from various angles, as shown in those samples. All videos are 29 frames and word occurs in the middle of the video. The word duration is given in the metadata, from which you can determine the start and end frames. The dataset statistics and samples are given in the table. This is the architecture of the current state-of-the-art model in this domain and what we are using for our base model and building on. It's the first to use mix-up as part of the data pre-processing, which was shown to improve results, and which we continue to use. Its front end consists of a 3D convolution layer, followed by squeeze and excitation resonant blocks of the extraction of informative features. These blocks outperform traditional resonance due to their use of attention mechanisms to model channel-wise relationships and enhance the representation ability of the model through the network. The backend consists of a bidirectional GRU. Additionally, the model incorporates label smoothing as a localization technique and applies word boundary in the pre-processing to narrow in on the word of interest in the middle of the video. Now, we'll cover additional aspects that we are adding to the model. In our road to implementing methodologies that might help in our model's performance, we found that lip alignment as data augmentation is crucial and is one of the promising approaches that we tackled, the inclusion of lip alignment to our dataset. Alignment has shown to improve results, as we have seen in the literature, and this also helps the model focus on lip movement, not pose variation. In this example shown, we take the original frame, apply alignment, then crop it. To perform lip alignment, we use a trained facial landmark detection model that was previously implemented in the temporal convolution neural network paper to produce 68 landmarks of the face. Then, using 3 XY coordinates, left eye, right eye, nose, we get a fine matrix with respect to the default neutral coordinates. Then, we perform a fine transformation on the image to deorient it, making the face upright.
So moving on to our implementation of spatio-temporal attention, our model directly generates attention based on the extracted frame level features, meaning that the computation is much simpler since our computation of the attention scores can be basically parallelized over the frames and not done sequentially like in previous implementations. This also means that we're not exhausting our GPU resources, and this was a very important aspect for us that we had to take into account given our model's complexity and our limited resources and time constraints. With regards to our feature extraction, we utilized the 3D front end that was already part of the original base code, which consists of a 3D convolutional layer, batch normalization, a rectified linear unit, and max pooling. And the extracted frame level features are then passed as input to both the temporal and spatial submodels. If we take a look at the temporal attention model, it's basically implemented using a deep architecture where each branch generates attention scores of the different frames based on the frame level features. So basically, the attention score of any given frame is just an indicator of the importance of this frame within the context of the video. Each frame's feature vector is also then passed to the sigmoid function to generate the attention scores. And this results in a temporal attention matrix. The attention scores are then multiplied by the frame level feature vectors to create a weighted feature vector, which is basically the temporal feature vector for the entire video, but taking into account the importance of each frame in the video. And if we take a look at the spatial attention model, we can see that it's employed using multiple spatial attention networks, which basically helps in paying attention to multiple parts of the frame by hopping over it multiple times. And this mechanism is set to improve the performance of the overall model by quite a bit. The spatial attention model also utilizes the frame level features extracted by the 3D front end earlier as its input. And it consists of 3 convolutional layers followed by a sigmoid function. And the attention matrix output of the sigmoid function is multiplied by the frame level features to output the weighted attention feature vector from the spatial attention network. And basically, to get the final feature vector, each spatial attention layer's output is then added to the temporal attention layer's output, and then those outputs are summed together to produce the final combined attention feature vector.
So now, moving to the new technique that we introduced in the backend. First, let's have an overview about knowledge distillation and its use in the literature in the area of deep visual speech recognition. So, knowledge distillation is basically the process of transferring knowledge from relatively larger model to smaller model. Some researchers refer to it as a teacher-student model, in which the smaller model, which we will call the student, learns from the larger model, which we will call the teacher. Knowledge distillation has been used and proven to be successful in several fields, like object detection and computer vision. So we decided to use it in our scope since audio recognizers tend now to be a quite mature problem, achieving relatively higher accuracy compared to visual speech recognition that is still relatively underexplored. So by using the knowledge transferred from the audio model to the visual model, we had a hypothesis that it shall improve the accuracy of our model. As we can see in this diagram, we apply knowledge distillation by introducing a new loss function that incorporates KD on frame level and the sequence level. But before that, we had to build our own audio recognizer, namely the teacher model, by training a sequence model that has a similar architecture as the visual model or the student model on the LRW audio data, with the feature extraction part inspired by Deep Speech 2 by Hadeel. For the frame level and sequence level KD, we calculated the mean square error between the visual and audio hidden states. However, it's worth mentioning that for the frame level KD, and due to the difference between the length between the visual and audio feature, we first had to map this correspondence by using a Gaussian shaped weighted average. So, to recap what was previously mentioned, here is our final architecture for our system. Most of the blocks that are being used have been proven to improve the model accuracy and generalization ability in the literature. So we used them in our model. Our main contribution are threefold. First, we added lip alignment in the pre-processing to allow the model to focus on the lip movement rather than the pose variation. Then we introduced spatio-temporal attention in the front end to better extract the visual feature. And finally, in the back end, we integrated knowledge distillation. We integrated sequence level and training level knowledge distillation to leverage audio data in the training time, a feature which has not been utilized in prior word-based work. Finally, here is our experimental setup. We use PyTorch as our main framework for this experiment. We used two computers from the university that supported dual GPU, and we trained our model for approximately 120 epochs. We also used a cosine decaying learning rate with an initial learning value of 3 × 10⁻⁻⁴. And finally, after incorporating spatio-temporal attention and the knowledge distillation parts, the model became quite heavy to train. So the maximum batch size that our machine could handle were 8 per GPU. Now I will leave you with Hadeel to show you our results and discuss it more.
So in this table, we're summarizing the final results achieved by adding the techniques we introduced earlier in the pre-processing, front end and back end to highlight their effects separately compared to our base model that achieved an accuracy score of 87.82% based on our own training. And as we can see in the table, our 3 contributions independently managed to achieve an accuracy score that is noticeably better than the base model, with the KD model achieving the best accuracy score and setting a new benchmark for the LRW dataset that is equal to 88.64%, which validates our initial hypothesis, and that's what our first paper submission was mainly about. And in the integrated model, the architecture was performing noticeably better than the baseline, as we can see in the following graph. However, towards the end of the training, it quite converged to a value that's very close to the base model. And our justification is that it might have got stuck at a local minima. However, unfortunately, we were unable to validate this due to the time constraints compared to the time needed for each experiment to run from start to finish, which is approximately about 15 days using dual GPU, which we tackle in detail in our second paper. However, in the demo we're about to demonstrate, the integrated model was able to successfully predict some words that even the KD model was unable to predict. So for our demo, we wanted to test the performance of our models using the videos that we created of our team speaking different words. So first, the pipeline takes the input video and then downscale it to be equal to the LRW input video size, and then crops the region of interest, namely loosely around the mouth. And then the cropped video gets fed into the model for inference. And here's one of the successful examples. And here are some more examples of the model's predictions, where in some cases it managed to predict the correct word successfully, while in others it mixes between the correct word and another word that has very similar lip movement, as we can see in the example below, where both Farah and Omar are saying the same word about. However, for the bottom left sample, the model wrongfully predicts the word significant instead. And as I mentioned earlier, although the KD model achieves the best accuracy score on the LRW test data, the integrated model was able to predict some words that the KD model failed to predict, as we can see in the sample, where the KD model predicts the word situation instead of the word operation. And here it's very noticeable how challenging it can be to distinguish between two words that have very similar lip movements. And now I will leave you with Marian to walk you through our reinforcement outcomes.
With regards to our reinforcement outcomes, we made noticeable progress towards our primary outcome, which is research. We've already submitted one paper describing our results for knowledge distillation to the International Conference on Computer Vision back in March. And we are finalizing our second paper describing our finalized integrated model to be submitted to the British Machine Vision Conference in June. As for our secondary outcome, we have plans to make our code open source upon finalizing everything after publication. During the course of our research, one of the main obstacles was finding relevant and accessible past works. As such, we hope to contribute to the future research by making our work as accessible as possible. The reason we're so adamant about this is because we believe that research in this domain has the potential to improve the quality of life for millions through the development of accessibility features in existing applications and the development of standalone accessibility applications. It must be noted that to reach our end result, we were met with a number of obstacles that threatened to hinder our progress. The first being the shortage of relevant available literature. Research relevant to ours was few and often poorly documented or inaccessible. There was also a shortage of relevant data sets with only a couple of decent labeled English lip reading data sets. Essentially, we only had the option of BBC's LRW dataset. We also decided to forego making our own data set early on because that would have required an unnecessary amount of time, and we already had access to LRW. So as of now, our model only supports English dialects and is able to recognize 500 classes of words. Additionally, the time constraints that were enforced upon us given the computational complexity of our problem, at times we had to sacrifice running some experiments in order to have time to focus on higher priority experiments, which means that we didn't get enough time to run as many experiments as we had hoped, which we believe might have improved our results even further. Finally, we experienced connectivity issues on the regular and had to keep restarting our training, which set us back significantly.
So even though this semester is going to an end, we still believe that our work's not finished yet. For example, going forward, we'd really like to be able to further extend the scope of our work by making our model more sentence-based. Initially, for the purpose of this thesis project, we decided that our model would be word-based, since sentence-based models tend to be more computationally expensive and usually take more time to pre-process and train relative to our current resources and our time constraints. We also hope to focus on further optimizing our model. Additionally, we also intend on leveraging more unlabeled data, which would subsequently also increase our available training data. And finally, we'd also like to make our research more tangible in the sense that we'd like to either incorporate such accessibility functions into existing applications or go as far as implementing our own standalone accessibility application. So to wrap things up, we believe that there is no research without action and no action without research, meaning that the primary focus of research should be to try to aid the progress of society and to try to improve the standard of living of its communities and its citizens, which has been our main focus since day one. These are our references. Thank you very much for watching, and we're happy to answer any questions that you might have for us.